Good morning, friends. Today we are going to talk about the unit number 3, that is photochemistry. I am Dr. Avinash Ramteki, Department of Chemistry, Devchan College, Arjun Nagar. So, friends, first of all, we just understand the definition of photochemistry, a branch of physical chemistry which deals with the study of chemical reactions that proceed in the presence of light, called as the photochemistry. Examples of photochemistry is the photosynthesis of plant, then chemistry of fusions, formation of ozone from oxygen in atmosphere, bioluminescence in fly, photography, phototropism, treatment of jaundice of newborn babies, and biosynthesis of vitamin D, photopolymerizations, photodegradation of polymers. So these are the examples of photochemical reactions. Now we just understand the difference between thermal and photochemical reactions. Thermal reactions takes place by absorptions of heat, but the photochemical reaction is takes place by absorptions of light. Rate of thermal reaction increases with increasing temperature. Rate of chemical photochemical reactions independent of temperature. For thermal reactions, the Gibbs free energy is negative, so the reaction is spontaneous. But for photochemical reactions, Gibbs free energy, that is delta G, may be positive or negative. Hence, the energy is continuous in thermal process or the reactions. Energy is quantized in a photochemical reactions. Examples of thermal reactions is the times of H2 plus N2 in presence of heat, that is formations of ammonia. And examples of photochemical reactions, it is H2 gas plus Cl2 gas in presence of light, formations of HCl. Law of light absorptions. There are two laws, very important. It is Lambert's law, and second one is the Beer's law. Lambert's law means when a beam of monochromatic light passes through the homogeneous absorption medium, when then the decrease the rate of intensity of light of with the thickness of absorbing media is directly proportional to the intensity of incident light. So we can write mathematically this law: minus di upon dx is directly proportional to the intensity of light, that is I. So it can be written as minus di upon dx is equals to k into I, where k is the absorption coefficient. So now log of I0 upon I is equals to a into k dash x, where k dash is the extension coefficient. Second law is the Beer's law. When a beam of monochromatic light passes through homogeneous absorbing solutions, then decrease the rate of intensity of light with thickness of absorbing medium is directly proportional to the intensity of incident light on a solutions. Here also the representation minus di upon dx is directly proportional to I into C. So that is the solution of concentrations of solutions. Minus di upon dx is equal to we can write k into I into C, where k is the absorption coefficient. These equations can be written as log of I0 upon I equals to a is equals to epsilon into C into x, where epsilon is the molar extension coefficient. So what do you mean by molar extension coefficient? That is, molar extension coefficient means the molar absorptivity or molar absorption coefficients is defined as the absorptions for a concentration 1 mole per liter of absorbing substances and unit thickness or the path lengths of this light radiations. Law of photochemistry. There are two basic law of photochemistry. Grottus dropper law, that is first law of photochemistry, and second one Stark Einstein law, this law of photochemical equivalence. So Grotthus dropper law or first law of photochemistry was stated only absorbed light is effective in producing the chemical change, while reflected and transmitted light does not produce any chemical change. Here the incident light, it is incident on a solutions, then it is reflected, absorbs some amount of the light, and some amount of light is transmitted. Stark-Einstein's law or law of photochemical equivalence, it was stated that each atoms or molecules of the reacting substances that take part in photochemical reactions absorb one photon to undergo the reaction. Hence, the energy absorbed by one mole of reacting molecule is called as the one Einstein's, or the energy processed by one mole of photon is called as one Einstein. Now, we just understand the quantum yield. The efficiency of photochemical reactions can be measured in terms of quantum yield. Quantum yield means the number of molecules reacting per quantum energy absorbed. It means that the number of molecules or the moles reacting per instance of energy absorbed, and it is denoted by phi. So hence mathematically can be represented as phi is equal to the number of molecules reacting in a given time to the number of quanta of light absorbed in the same time, or phi is equals to number of moles reacting in a given time to the number of Einsteins of light absorbed in the same time. If Stark-Einstein's law is strictly obeyed, then quantum yield of reaction is equal to 1. For example, the reaction between SO2 thionyl SO2 plus Cl2 in presence of light, that gives the SO2 Cl2. But for many, quantum yield of reaction is either greater or less than 1. So this condition for the unit quantum yield, that is phi is equals to 1 of photochemical reactions, that is if Stark-Einstein's law is strictly obeyed, then quantum yield of reaction is equal to 1. This is because of the some of the reasons, like all the reacting molecules should be initially in same energy state and hence equally react. The reactivity of molecules should be temperature independent. The molecules in the activated state should be largely unstable and decompose to form product. So the examples of this SO2 plus Cl2 in presence of light and formations of SO2 Cl2. So here the quantum yield is equals to 1. So it means phi is equals to 1. Reason for high quantum yield of photochemical reactions. So according to the Stark Einstein law is not strictly obeyed here. Hence quantum yield of reactions may be high, and because of this some reasons, formations of intermediate product acting as a catalyst. If a reaction is exothermic, then heat is released. This heat may active other molecules and they react without absorption of radiation. Third reason for the high yield of quantum yield for photochemical reaction is that the active molecules are produced, right? So after the absorptions of radiation, then they may collides with each other, or these two molecules all collides to each others and the active them, which converts into the reacting molecules, right? So the atoms or free radicals may start to series of chain reactions. For example, the H2 plus Cl2, it interacts with this H2 molecules to the Cl2 molecule in presence of H nu or the lights, and it formations of first is formations of radical and then it form a two molecules of hydrochloric acid or HCl. But here the quantum yield for this reaction is 10 raised to power 5. So it means that the quantum yield is not equals to 1, it is greater than 1. So this is these four reasons how the quantum yield for this photochemical reaction is increases. So now reason for low quantum yield of photochemical reactions, right? So if the Stark-Einstein law is not strictly obeyed, then the quantum yield of reactions may be low than that of the one. So because of this, some reasons are responsible to lower the quantum yield of photochemical reactions. The primary photochemical process may get reversed. Second, excited molecules may get deactivated before the formations of product, right? Then the collisions of excited molecules with non-excited molecules may cause the loss of energy of excited molecules. So next one, the dissociated fragments may recombine to form original molecules. Energy absorbed by the molecules may not be sufficient to excite the molecules and start to reactions. For example, if you had taken examples of malic acids in presence of 30 quanta of photons and it formations of fumaric acid just to change the orientation of hydrogen and the carboxylic acid group. And here the quantum yield for this reaction it is phi is equals to 0.03. It means that so 0.03 it is less than the unity. Hence this is the 5 reasons how the quantum yield of photochemical reaction is low. The next concept it is the spin multiplicity. The term symbol 2s plus 1 is called as a spin multiplicity, where s is total spin and this capital S is total spin. Singlet and triplet state. This concept is very important. In ground state, all the electrons in a molecules are paired. Therefore, total spin of a molecule is equals to 0. Suppose at a ground state, both the electrons in the lower level energy level, the multiplicity is equals to 2s plus 1. It means that 2x or 2 into s is equals to 0. So into 0 plus 1 it will come, that is 1. So singlet ground state. Now in presence of light, one electron get excited into higher energy level, then the multiplicity of this it is 1. So again it is also called as a singlet excited state. Or if the excited electrons does not change their spin, so it is aligned with the first electrons which is present in the ground state energy level, and here the multiplicity of this it is 3. So it is called as triplet excited state. For ground state, S is equals to 0. So 2s plus 1 is equals to 1 and called as singlet ground state. So it is represented as S0. When electron excite to higher energy level, so it means change their spin, retain as it is. If the spin of electrons retain as it is, S is equals to 0, therefore the multiplicity 2s plus 1 is equals to 1, right? Such a state is called as the singlet excited state. So it is represented as S1. If the spin of the electron changes, S is equals to 1, therefore the multiplicity to S plus 1 is equals to 3. So such a state it is called as a triplet excited state, and it is represented as T1. So in the first, second and third singlet states are represented as S1, S2 and S3 respectively, while first, second and third triplet states are represented as T1, T2 and T3. Now we just understand the very important concept in this photochemistry, that is the Jablonski diagram. When the light is absorbed by system or the molecules, then photochemical reactions in taking place. But sometimes light absorbed by the system does not undergo the photochemical reactions and give various other phenomena. The various phenomena shown by the system after the absorptions of light represented by diagram called as a Jablonski diagram. With the help of this Jablonski diagram, we can explain some the phenomena, right? That is the non-radiative transitions and radiative transitions. So now, non-radiative transitions means the transitions which do not involve the emissions of any radiations are called as non-radiative transitions. And the non-radiative transitions involve two types of transitions. First is internal conversions, that is the activated molecules return from higher excited state to first excited state. For example, S3 to S2, S2 to S1, T3 to T2, T2 to T1. Now, in such a case, energy of activated molecules loses their in the form of heat. This energy, this process is called as internal convergence and it is represented as IC. This process occurs in less than 10 raised to power minus 11 seconds. And the second process or the type of non-radiative transition, that is inter-system crossing, and it is also called as ISC. The activated molecules returns from higher excited state to the different spin state, that is S3 to T3 and S2 to T2, S1 to T1. This process called as inter-system crossing, and also molecule loses energy in the form of heat. These transitions are spectroscopically forbidden, therefore occurs relatively at slow rate. So this is the simple diagrams which we can very much understood the Jablonski diagrams and the interconvergence and inter-system crossing of electrons or the energy from S3 to S1, S3 to S2, S2 to S1, or S0 to S3, S0 to S2, S0 to X1. So singlet ground state to singlet excited state. Excitation is taking place by the absorptions of light. Again, the same way, this excited singlet state or the electrons, it is the lost their energy or loses the energy and comes to the ground state or the lower energy level. So if S3 to S2, S2 to S1, so it is simply called as the internal convergence. And if the S1 to S0, by losing some amount of energy, this is the phenomenon it is called as fluorescence. And if the intersystem crossing of energy between the S3 to ST3, S2 to T2, S1 to T1, and from T1 to S0, this is, or from S0 to T1, it is called as the phosphorescence. Now, the second types of the transition, that is the radiative transitions. The transitions which involve the emissions of radiations are called as radiative transitions. In these transitions, activated molecules return from the singlet excited state, that is S1, and triplet excited state, that is T1, to the ground state, that is S0. Radiative transitions involve two types of these transitions. One is the fluorescence. In this fluorescence, from the energy, it is losses from S2 to S1 to S0. So, this activated molecules from the singlet excited state S1 to ground state S0 is called as fluorescence. These transitions are allowed transitions and occur in about 10 raised to power minus 8 seconds. And the second transition, that is the phosphorescence. In these transitions, the emissions of radiations due to the transitions of activated molecule from triplet excited state, that is T1, to ground states S0, that is called as phosphorescence. These transitions are forbidden and occurs at slow rates. Fluorescence, it is the emissions or radiations due to transitions of, we know that this, of activated molecules from singlet excited state S1 to ground state S0. Fluorescence starts immediately after absorptions of light. So the fluorescence stops as soon as the light cut off. But, or in fluorescence, wavelength of emitted light is usually greater than that of the absorbed light. Different substances in the fluorescence light of different wavelength. So it is shown by liquid as well as solid. And examples of organic dyes such as eosin and fluorescence, vapors of sodium, mercury, and iodine, inorganic compounds such as uranyl sulfate. So these are the examples of fluorescence. Now move towards the phosphorescence. It is the phenomenon or the emissions of radiations due to the transitions of activated molecules from triplet excited state. So that is T1 to S2, and it is called as simply the phenomenon of phosphorescence. So phosphorescence, it is continue even after the incident light is cut off. Thus magnetic and dielectric properties of phosphorescent substances are different before and after the luminescence. This is due to the change in spin of electrons. The phenomenon is mainly shown by solids, for example minerals, ruby, zinc sulfides, sulfides of calcium, barium, etc. Now we just understand the photochemical reactions. There is some kinds of photochemical reactions. It is photosensitizations. Some chemical reactions do not take place by direct absorptions of light energy, but when third substance is added into this, then chemical reaction is start. The third substance absorb the light energy and then transfer this absorbed energy to the one of the reactant molecules, and therefore the chemical reaction it is start. That third substance added in the reaction does not undergo any chemical change. It only acts as a carrier of energy. The substance which added to a chemical reaction helps to start the photochemical reaction, but itself does not undergo any chemical change. It's called as a photosensitizer, and the process it is called as photosensitizations. The examples of this reaction it is photosynthesis in plants. In these reactions, the carbon dioxide from the air and the water molecules in presence of as a sunlight, and the plants having some chlorophyll pigments, the specifically that is the chlorophyll A. So in this, the state of reaction, the CO2 and H2O, it is converted into the C6H12O6, and this is the carbohydrate. So this carbon dioxide and water vapor molecules in the presence of air and chlorophyll pigment A, and this absorb the energy. Chlorophyll pigment A, it absorb the energy and transfer. So after absorptions of energy, it transfers to the carbon dioxide and water molecules. And now this carbon dioxide and water molecules react to each other and formations of this fruitful product, that is the carbohydrates. So therefore this photochemical reaction, it is an examples of the photosensitization reaction, because the chlorophyll A, it is acts as a photosensitizer. The second examples of this one, it is decomposition of oxalic acid in presence of uranyl sulfate. In this, uranyl ions absorb the light energy and then transfer to the energy to oxalic acids. Therefore, the oxalic acids undergoes the decompositions, right? So, this decomposition formations of a product like the CO2, carbon monoxide, carbon dioxide, water molecules, and ions of uranyl sulfide. This is the second examples of these photochemical reactions or photosensitizations. Now, the experimental determination of quantum yield. So, here is the simple apparatus of to detect the quantum yield. Here is the light source. After then this lens, then the monochromator, then reaction cell, and the detector. So with the help of these simple instruments, we can able to determine the quantum yield of photochemical reactions. So now we measure two parameters, and that parameters is very important. One is the number of moles of substances reacting in a given time, that is the rate of reaction, and second one, the quanta observed per second. So this apparatus used for the measuring the above two parameters, it consists of light source, sunlights, arc lamp, mercury vapor lamps, tungsten lamp, etc. So this is used as a source of light. The monochromator of this instrument is used to select the particular wavelength. Color plates, prisms or gratings are used to monochromators. Reaction cell. The reaction cell is made up of glass or quartz, or it has optically plane window for the entrance and exit of the light. So reaction cell is placed in thermostat to maintain constant temperature. And the last part of this instrument, that is the detector. So the role of detector, it is very important because it detect incoming lights coming from the reaction cell falls on the detector, and it measures the intensity of transmitted light. First light pass through empty reaction cell and its intensity is measured. So then light is passed through the reaction mixture and its intensity is measured. The difference between the two readings will give the intensity of light absorbed in the reactions. Generally, thermophile or chemical actinometer is used as a detector. So this chemical actinometer contains solution which is sensitive to light. When light is falls on the solution, chemical reaction starts. Extent of chemical reaction is directly proportional to the intensity of absorbed. The most common chemical actinometer used as a uranyl oxalate So it consists of 0.505 molar oxalic acid, 0.05 molar oxalic acid and 0.01 molar uranyl sulfate solution in water. So this oxalic acid decomposes photochemically in presence of uranyl sulfate. So therefore uranyl ions acts as a photosensitizer. The reaction takes place as, so these uranyl ions in presence of light form the excited or the absorbed light energy, these uranyl ions. Therefore we are represent this uranyl ions, that is asterisk. Now this excited uranyl ions, it's in presence of or it treated with the oxalic acids, formations of CO2, CO and water molecules. So the remaining amount of oxalic acid can be measured by titrating against a KMnO4 solution. The extent of decomposition of oxalic acid is proportional to intensity of light absorbed. Thus knowing the number of moles reacted and the number of quanta absorbed, quantum it can be determined. So here the theoretical part of this photochemistry units is completed. We will see the numerical problems in next video. Thank you very much.